And I think everyone in here now would have sat downstairs with Roberto and gone through the training. So I wanted to make sure that I'm not repeating a lot about what he said, but actually some questions were about when should you use reflectance versus transition versus ATR. I've got that in here. What sort of filters are good for FTIR as well? So it's a bit more generic about improving. And then towards the end of the presentation, I'll talk a little bit about what's coming next in the future as well. You'll actually be the first people in the world to hear this. So very briefly, I know we've spoken about it in a previous conversation, so I'll go very quickly. But for those that haven't used an FTIR microscope, think about an optical microscope that also has an infrared capability. So you can see the microplastics on the filter, but then you can actually inquire as to what is the nature of those, what sort of polymer they are. You can see we use it for wider than microplastics. Actually, our biggest customers are normally in polymer laminates or defects in polymers. You cut across, and then you see in each of the layers what is in there using the infrared analysis. So if there's a defect there, we can very quickly analyze it. But microplastics is probably the most growing area in our FT microscopy portfolio. So I put this slide in just to explain. So a lot of people are used to macro IR, and you can see there, we give an example on the left-hand side of the screen. Once you're talking about maybe 1 centimeter or whatever, you can do macro analysis. And actually, I saw your presentation earlier, Andrea, where you're showing the ones you could see. Very simply, you could put that on an ATR of our product, like Spectrum 2, but any FTIR, and you can do analysis and find out what that polymer is. Once you start collecting the microplastics, that is when you have to move into a microscope. Now you can break those into 2 areas. There's infrared microscopes and infrared imaging systems. With a microscope, you do the visible imaging, and then either you or the computer can then identify, the software can identify the particles that you want to, you can see visually on the screen, which then you can do analysis for the chemical makeup. In imaging, the system analyzes the whole image and takes an infrared for the entire space that you define, or the computer thinks that there is something of interest there. I'm going to talk a little bit more about actually the point detection, the micro IR today, but there is a little in there on imaging as well. So this is the entire workflow. Obviously, you begin by collecting the samples, then you clean them up in some way, do some pre-processing. I saw some of the presentations this morning. Forgive me, my Serbian is not great, but I did work out from the conversations earlier and from the slides that actually we've already gone through a lot of the cleanup already. You filtrate, and then you do your analysis on that filter. You can actually remove microplastics from the filters and put them onto some ways of analyzing in the infrared as well, but you might lose samples there. So typically it's done on filters. And then you've got the decision of transmission, reflectance, or ATR. And obviously the technique you use, maybe you've only got a few microplastics there, point mode is better. If you have a filter that has a lot of microplastics in it, typically we'd recommend doing imaging. And I'll talk about those as well as we go through. So I thought I'd show a very visual representation. It's actually a very simple workflow when you take a step back. You collect the microplastics on a filter. You can see in the bottom left there that you load it into underneath the microscope. And then in this case, you see we've done a imaging analysis that's automated in our Spectrum 10 software. You can see it's picked out all the particles that you can see on the filter. And then what you want as an output is the dispersion of polymers that are present. And then you also want their particle sizes as well. And both can be done in our software. So the first thing you have to consider is the filters. And you can see we've put them up here, different diameters, different pore sizes, and also different costs. And unsurprisingly for how the world always is, the silicon one, which is the most expensive, is the best for IR. You'll see it's actually good in reflectance and transmission. But, gold-coated polycarbonate is also very good. It depends on what sort of samples you have, how many of them are on the filter, as to what will be the best filter. So I'll take you through a little about what we're going to show. So here's some real data here from our microscope. And just to give you an idea, So PVDF filter on the left, and then the gold-coated polycarbonate filter on the right. Now, why the PVDF filter is not so good, you see that there is a lot of extra information you're getting from the filter in your infrared. Obviously, you don't want your microplastics masked by the filter itself. And you can see that actually we've taken that filter and done our analysis in transmission and reflectance. You would argue actually for reflectance is a little better there, but there's clearly a signal. So not ideal for infrared analysis. If, however, you use a polycarbonate filter, you can see that actually in reflectance there, you have no signal, and you're getting a good amount of intensity from there. So that's good. If you look at the transmission, there's a separate issue there, is that the light can't penetrate through the filter. So then you get no signal at all. So in this case, excellent for reflectance, terrible for a transmission. So the filter affects which analysis technique you should use with the infrared. And so we put up a nice little graph here that shows through the wavelength range what is a good filter. And as I said, if you look in transmission or reflectance, silicon is excellent, but is the most expensive. If you look though, polycarbonate gold-coated, excellent in reflectance, not so good in transmission. And then you have PVDF, what I spoke about earlier. You can see actually that there are areas of the spectra in transmission where it's actually very, very good. So in this case, if you're using PVDF, I said it wasn't great for reflection. It's bad for reflection. It's not great for transmission. You can see that if you focus on a small wavelength range, you can use that as well. So it's not exact rule that you can't use any of these filters for certain types of analysis. Sometimes you can just narrow the wavelength range that you're looking at and still be able to do the analysis as well. As I said, you can also take the particles off the filter and put them onto an IR compatible window or a low E glass slide or gold mirror. There are actually these microscope slides that you can get called Keevely slides that actually have a reflective backing, so you can do reflection in them. It's not something we recommend because obviously there is an extreme danger that you can lose some of your particles as you're trying to transfer them. So generally, we advise to do the analysis on the substrate or on the filters themselves. So now you've chosen your filter, you now have to think about what sort of analysis technique that I'm going to use. And so 3 examples. If you've got say the sample is here, I'm sorry, I'll put that so you can see it on the camera as well. Here's my sample. Reflectance, as you can imagine, you have the particles sitting on the surface, you're reflecting the light off. Transmission, you are hitting it through the samples. And for ATR, we have a little crystal that drops down and actually touches the sample. So ATR, you get the best signal. You can actually see here, it's in the bottom right. You can see you get a very good signal from the sample. The problem you've got is actually when you move physically the crystal down and you make a touch of the sample, you can actually move that and you can actually change your sample. It's not a big risk, but it is something that can happen. So actually what I would say is that although drop-down ATR is very popular with a lot of our customers, generally I would say that transmission or reflectance is more common. Both of them are much easier to do and faster, but they have problems. And I think actually, if you've been downstairs with Roberto, he actually showed a good example. Reflectance, for instance, works really well for microplastics, but if you have a bigger particle, so something on the higher end of a microplastic, actually it doesn't work so well, and that's where ATR plays a better role. If you only have a few smaller microplastics on there, transmission does work very well. But once you start to get sort of thicker, larger samples, again, you don't get the signal through, so it can be a problem. So generally, if you can add an ATR a drop-down ATR to your microscope, you do generally get the best results. But what I would say is if you're going to be doing filters with a lot of microplastics on them, so if you're doing bottled water, for instance, I'll show an example later, there's maybe 1 or 2 microplastics in there, maybe most sort of 20, something like that. If you're collecting from a river that's polluted, the whole filter will be full. And then ATR is not a good solution. You'll do imaging in either reflectance or transmission. You can do array ATR as well, but generally it's more reflectance and transmission in imaging. So you now know what technique you want to use. For infrared microscopy, there are basically, I put 4 up here. Actually, one of the speakers this morning reminded me there's now a 5th. So point mode is obviously you find your microplastic and you say, analyze this infrared, what is it? Is it polyethylene? Is it polypropylene? You can also actually say, I want to do a map. So 20 places where I want to see across here, what is the microplastic? And you can come back. Then you move into imaging and you can have linear imaging, which is what we have in our Spotlight 400 product. And what you're doing then is taking an array of that. So you think about, you're looking over the whole filter itself. What I'll say is there's also focal plane array imaging, which is a bit faster but more expensive. But what actually, it just shows you how quickly technology moves along. This morning, actually, someone pointed out there's also QCL IR imaging as well. And that's even more expensive, very, very expensive. But again, you can then do it even faster. What I would say is QCLs, or quantum cascade lasers, are a source where they actually only look over a very narrow range and they're tunable. So you have to buy a lot of them to make a full wavelength range, which makes them very expensive. So they have advantages of speed, disadvantages of a lot of expense. So I'll start giving a couple of examples now as to what we've done at PerkinElmer. And this was, although I'm based in the States, a lot of my applications team is still in the UK. And so we had a bottled water brand. They're Swiss, you probably guess who it was. And we were doing some analysis for them. And you can see here, this is the visible image. There's very few microparticles on there. I think there was like 5 or 6, something like that on bottled water. Look at the bottom right. This was quite interesting, is that we thought there would be more microplastics in the water supply in our lab in the UK. But when you look at it, there was actually a lot, quite worryingly a lot actually. And this was just purely, we weren't expecting to show this as a real example. We were just using it as a base. And we realized actually our water supply in High Wycombe in the UK was actually pretty bad. But this is the workflow they went through. So you select whether you're doing point mode or imaging, you perform your IR data collection, then you analyze the data. And so when it comes to data analysis, as I pointed out, once you have the visible image, you see on the left, either you can say, all right, I want to pick this particle or this particle and find out what it is. Or in this case, the software has actually automatically analyzed the sample and said, all right, I can see 1, 2, 3, 4, 7 particles on there. I will go through, I'll do an infrared of each of them, and I'll tell you what they are. You can see the output. And you can either have 7 spectra, or if you've got 200 particles, you can ask it to give you a breakdown of the percentages of how much is present. Now, when you come to imaging, and I won't go into a lot of detail because I know if you went downstairs with Roberto earlier, he talks a bit about this and he shows some examples. But here you can see the computer has gone across and we've taken a whole array and we've built up a map of the water sample. So you can see where we've got blue, there are no microplastics. Where you see light areas, there are. And we're just mapping that based on the infrared wavelength. So that we're using the wavelength to identify where there's microplastics and where there isn't on the filter. And then what we can do is a mathematical technique called PCA, or principal component analysis. So on the left there, you see the average absorbance. So you can see where the particles are, but obviously you don't know what they are. You can also tell that they're different. If you then do PCA analysis, you can break it down and work out which ones are polypropylene, polyethylene, whatever polymer is present there, polystyrene. And you see in this case, I have to say, I don't know which score 1 and score 2 are, but you can see with the combined scores as well, we've separated. Score 1 is one type of polymer. Score 2 is another type of polymer that you can see actually, we haven't got the blue here, but there's a third type of polymer. And in the combined scores, you can then do analysis and say, all right, this is 60% of the microplastics here are polystyrene, 30% are polyethylene, etc. So PCA analysis is a really good tool once you've started to do imaging to then mathematically work out what is the dispersion of polymers that you've found in the water sample that you've collected. What's the time? Still got time. Good. Now, for those that that have used microplastics analysis in the past using FTIR, our software can do a lot of the analysis in the back end, but I know that there are third-party softwares that people like. Now, what I will say is that actually Puracy have actually gone out of business now. I heard quite recently. So whilst some people still use Puracy software, that's no longer a software platform you can export into. Simple, though, is very common in our industry. And it does a lot of what I just described to you that we can do in our software. But generally, you know, a lot of people, they might use multiple techniques. They want to use a third-party software. And Simple is pretty much across the industry used quite regularly. I know in the UK and in sort of Central Europe, it can take the output of a lot of instruments, including our own. You can put it in here and it will automatically give you the dispersion of polymers and their particle sizes. So this is quite an interesting bit, and it's why I'm in Europe at the moment. So I wanted to talk to you a little bit about what's coming in the future. And actually, what's interesting, you are the first people in the world to hear this outside of PerkinElmer, because we've been working on this for 2 years. And this will be a product coming out very soon called Spotlight Aurora. And we actually designed this for microplastics. And what you'll hear is from a lot of vendors, you'll hear people say, all right, well, you know, I'm going to make a better IR. So you spoke about earlier, I'll have a focal plane array. I'll have a quantum cascade laser. Essentially, you're making the infrared analysis part a little faster. But when we looked at it and said, what takes the most time? If you're doing point detection, what takes the most time is finding the samples, because you have a very accurate optical camera, and then you have to come out of focus, find the sample. So what we did was we put 2 cameras in this product. Now, as you know, Britain doesn't have a queen anymore, but she's still on the stamps. So we did the analysis on a stamp of the queen. But you can see here that we've got a wide field camera now that I showed on the right. On the far left is what we used to have as a camera. You can see on the far right, you can see the queen. And then we say, we've identified a blemish on her cheek. Then we use a high definition camera, so we have 2 of them, to then look at that blemish. And then you can actually see in the top left, that box, there's a bit of a gap between 2 of the dots on the stamp. That is the blemish that you can see in the high level. So what that means is that it's actually 13 times faster for you to identify problems. And what's nice is that we then combine that. Oh, actually, no, before I talk about the combination, I just want to show you how much faster it is. So if we take a microplastic filter, say in this case, we're looking at a 1 by 1 centimeter survey. For our older instruments and for actually a lot of the instruments that are on the market right now, this is how long it takes to analyze. Oh, that didn't work. Let's try again. There we go. So this is what you see in the past, and this is how the visible image is made up. So it goes across. It takes 15 minutes, so we didn't really want to just sit here and wait. It would be pretty boring. So we cut away, and it will come back in about a second. So now we come back. It finishes the visible image. So 14 minutes. This is the point now where you do either the automated or manual analysis. All right, which of these particles? This is our new instrument. So using the combination of the wide field and a new high definition camera, this obviously we sped it up a little, but you can see the timer here on the left. You can see that we're already halfway after about 30 seconds. And within, I think, 1 minute 15, I think we are, or less than that, 1 minute 14, we've already done the analysis. So what we've looked at is what would be the rate limiting step. So the upshot is that you can do analysis much, much faster than you could in the past for other FTIRs. And then actually we looked at the microplastic workflow specifically about where we could improve things. There's also something else we added in there. So any of you that have used Raman spectroscopy or Raman microscopy, you know that some microscopes do a thing called Z stacking. I'm in America now, so Z stacking. I've got to translate. And why that's useful is I've showed a pharmaceutical tablet here. On the top left is what you would see from a normal microscope. On the top right is what you see from spotlight aurora. And then we've got a kind of visible map then. And what you can see there is information in the Z direction. Now you might say that's nice, but why do you need that for microplastics? Well, if you do Z stacking, what you're doing is taking analysis at different heights. And why that's important is that if you're doing microplastics, you would have heard downstairs, you have to have a flat filter, or the filter cannot be bent in any way. If you do Z stacking, it doesn't matter. You can stack through, take images through, say, 1,000 microns, and then it will optimize the best picture at each point. So if this microplastic is higher than this microplastic, what you'd see normally is one's in focus, one's out of focus. If you do Z stacking, what it'll do is the computer will then make it look like they're both the same, and you'll see it optimized. We do that concurrently with this as well. So what I'm trying to say here is that what we did was we looked at all instruments now have very good infrared analysis. What we're going to do is optimize the optical part so that it can be a much faster, more reliable workflow. But we didn't just stop there. We've got a microplastics guided workflow now. Anyone who's used an IR microscope, there are a lot of different parameters that you have to optimize. Not everyone's an expert. If you look on the far left and the far right, there's a little box that comes up that guides you as to what you should optimize for your sample. So what this allows you to do is build a macro. We have those in with our Spectrum 2. We've not had them for the Spotlight before. That allows you to build something that you can do the same analysis day in, day out. You can just click go, do the analysis, come back, and you'll have what polymers are present. So for maybe once we move away from the research area and get to testing labs analyzing it, an analyst then doesn't have to understand microplastic workflows in a lot of detail. You would just be able to do the analysis and find out the answer. So I think I'm about 5 minutes early, maybe. But to summarize, so FDIR microscopy is an important technique for looking for microns from a few microns in particle size. I often get asked, what size can you go down to? In theory, you can get down to 5 microns. In reality, it's more like 10 microns really for FTIR microscopes for really good data. You can do 5 microns. You must do appropriate sample preparation to eliminate matrix interferences. That's very important for good results. And then optimize your filters for the type of analysis you're going to do. So silicon works for all different types of analysis, but you can go use gold-coated polycarbonate for reflectance, or aluminum oxide, say, for transmission. And then finally, optimize the sample throughput. So basically, as a rule of thumb, if you are going to be doing a lot of microplastics that you're only going to find 1 or 2 on a filter, then probably you just need a point mode system. And downstairs you saw one that's a Spotlight 200. If though you're going to do a lot of samples, say polluted rivers or something, you're going to see a lot of microplastics. It is better that you go for an imaging system, and that's a Spotlight 400. And both are optimized for that. And at that's all I had. So I just want to thank everyone for their attention. And yeah, thank you. Oh, questions? We can have some questions. We have time.
Yeah, that's what the workshop is about. Please raise your questions. We have Galina here with us. So please speak up.
Okay. You can ask in Serbian if you want. Someone will translate for me.
Thank you for a nice presentation. I have one question regarding the reflectance mode.
Yeah.
Is it really useful when you have the particles that are like irregularly shaped? They don't have the smooth surface, because we were trying something like this and it was not quite successful.
Yeah, it does depend. It's a good question, or a good point to bring up. It does depend on the orientation of those polymers. If you have a lot of irregular ones, you start to get interferences, and then actually it's not ideal. And I probably should have brought that up, is that generally if you have if the dispersion of polymers You saw, I think, a slide earlier where people talked about different, sometimes you get orbs, sometimes you get fragments. If they're all the similar type, actually reflectance works well. It's when you have different types, you actually start to get interference from the two different samples. And then reflectance is not good. You would do transmission or ATR. That's a good point.
Anyone else?
About the nice presentation. I'm interested more in the principle of Z stacking.
Yes.
That you mentioned on the new microscope. How does it, when you have a material like which is thick, and in what mode does it do the Z stacking?
Yeah, it's as you say, thick sample, it has to be reflectance. So you're only obviously seeing the edges. But what's quite nice is that I don't have them here, but we did a lot of analysis on, say, you know, a UK penny. If you look at the penny coin, it's got a little gate on it with the feathers. We can look down actually, and we can see the slope of the side. But yes, reflectance, because if it's a thick sample, you can't get transmission through the sample. But I'm glad you noticed that. It's a good point.
Galina.
Just one question out of curiosity, because we have seen we're also showing the data from Obama's study on the laboratory study for the microplastics. Did you go maybe more in detail, or you had maybe like a chance to look into these results and see like which FTIR equipment was used? Was it like from Hammer or from other vendors? And did you check maybe between different laboratories which are using your equipment, the confidence levels, for example?
Yeah, I mean, obviously I'm going to be biased, so I'm not a good independent regulator. But I can tell you, actually, we do a lot of work with the National Oceanographic Centre in the UK in Southampton, and they are obviously unbiased. And there's, you know, in my ideal world, everyone would have PerkinElmer equipment. The reality is people don't. And when they look at the results around Borodin studies between them, generally the advice I gave counts between all of them. You know, it's with FTIR microscopy. You know, I'd love to tell you that honestly, unless you buy a PerkinElmer equipment, everything else is bad. But that's not true. The reality is that how the science that you put behind it and how you prepare the samples and how you analyze them, which is why I was talking about it, counts for a lot more than the difference between the vendors. So if you know, a lot of the time we get questions about, you know, I can't get any transmission through the sample. Not so much actually microplastic, but we do have that mission, so they only get a small amount of sample. So I think the answer to the question is, I think there isn't a lot of difference if the science is good behind them.
Just additional question: how do you do the background subtraction, for instance, so that you're also then, especially in microplastics, then to your customers, you propose them like have these blanks, the procedure blanks, this type of. So
if you didn't go downstairs and see Roberto's demonstration. Oh, you saw he was looking in between on the filter. He was using that as a background to subtract. That's for filters. That's what people typically do, and that's what we recommend, is use the filter as the background. But there are people that use different backgrounds. Actually, some people will try and you know, subtract a polymer background to try and just look at, is there intensity or not based on one polymer. It's not something we recommend. We generally say a neutral background and then subtract. And then once you've done that, the computer automatically does it. Some people actually, you can switch that off in the software. So you need to run a background or it won't let you run the sample, you know, the sample. However, some people like to see a background subtracted. Some people like to see the data raw. The data's there, you can decide for either. And I think, again, that would be the same between all vendors. I don't think there's any difference there. I think there was a question at the back.
Thank you very much for a good lecture. We got a lot of information from you. I have a probably technical question. When it comes to fibers, which mode would you prefer and suggest? Because what we have seen in our results.
Then you have more intensity, so you can do that larger array even faster. But it just depends on the type.
Okay. I think we have surpassed the time. So thank you very much, Mr. Robert.
Thank you, everyone.
Okay, so our next speaker is Dr. Milica Velimirovic from Vito. She earned her PhD in applied biological sciences from the University of Antwerp and has built her career at leading institutions in Belgium and Austria, including Vito, the University of Vienna, and the University of Ghent. She is currently a Marie Curie postdoctoral fellow at Vito, the Working Group 7 leader in the Cost Action Priority, and project coordinator of the EU-funded SSBD4CAM project. This workshop will highlight the latest analytical tools and methods for identifying and characterizing nanoplastics. So she will go even a bit further than we have been so far, along with the real-world case studies demonstrating their application. So Milica, the floor is yours. You can be here after for questions as well.
Okay, no problem. Hvala Andreja na pozivu. Znači, ja ću imati moju prezentaciju na engleskom jeziku, ali naravno pitanja možete uvek postaviti i na srpskom. Ja sam inače oficijalno u Srbiji na godišnjem odmoru, ali nisam mogla da odbijem ni Andreju, ni Aleksandru da dođem ovde i prezentujem šta mi trenutno radimo i koji je naš istraživački cilj vezano za mikroplastiku i najviše nanoplastiku trenutno. So maybe I switch now to English. Today I want to present you a few case studies, what we have done in recent years from macro to nanoplastics and beyond in terms of the analysis and some different analytical tools that are generally used in the laboratory for the analysis, especially of the microplastics. What I want to say that I'm coming, actually I just finished my Marie Curie postdoctoral fellowship at the Flemish Institute of Technological Research. And basically now I have a research position. Vito is in Flanders in Belgium, in the northern part, and it's an independent research institute which is focused on accelerating the transition to the sustainable world. We are quite a large institute with more than 1,000 employees. It's highly international with a huge number of publications and patents per year, and also we have 11 sites on 3 continents. I'm coming from the Central Analytical Laboratory. Basically, we are serving customers outside of Vito. We are a reference laboratory for the Flemish government, but we are also serving all the researchers in Vito with their specific topics when it comes to the analytics. Our team is around 30 people, mostly analysts who have around 20 years experience in the analytics. Of course, we have also like our program manager with research team, which has like 9 researchers. We have a postdoc and 2 PhDs. I have to say that both PhDs are now working on the nanoplastics topic, for example. How we started with the nanoplastics analysis. So basically we started with the integration of all the equipment that we have in-house, which is mostly based on the nanoscience method. So you see, in order to characterize the nanoparticles, Previously, there were metallic nanoparticles, but again, the story is the same. You have to characterize them in terms of the shape, size, distribution, structure, composition, concentration, which agglomeration state they are, and so on. In-house, we have like quite large equipment. I'm just like, so basically, in our lab, we have most instruments which are used for the nanoparticle characterization, and we tried to extend it a bit further for the microplastics characterization as well as the nanoplastics. If you have like specific questions for the certain instruments, you can later on ask me, but this one is just like to show you like that different instruments can serve us for different purposes and different analytical questions that we have. The first study that we had was actually on the plastic debris, and it was the case study at the Seychelles estuary. So this is like where the part comes from macro to the nano and beyond. What we did in the Seychelles estuary, we monitored the plastic debris in the spring, summer, and autumn in 2018 together with the University of Antwerp. We were using the anchor netting for taking the samples at different spots at the Scheldt River. So this is basically like the estuary, which is connected then to the North Sea. At this specific period of time, we collected more than 12,000 plastic items, which were then categorized. But at a certain point, we also took the subsamples, and at that time, we did try to do the FTIR spectroscopy to check what is the plastic polymer composition depending on the plastic itself. Of course, as we all expect, the polypropylene was one of the main common plastic materials in the debris, as well as the polyethylene. I expect a bit more polystyrene, but of course in the hard plastics still the polystyrene is like the one which is most abundant. What else we did? This is what also Andrea said, like, oh yeah, who was counting the plastic? So basically, yes, the plastic was counted and separated based on the size category. And then, of course, we also weighted the plastic. So for 3 seasons, for all these more than 12,000 pieces. And basically here you can see that this kind of the distributions, and I think that you already now know that counting the particles and weighing them, that we don't have the same results. So this is what we have to deal in microplastic research, but I think this is also something which is coming also to the microplastic research, because we have like particles which are almost 1 millimeter, and also we have particles which are 1 micrometer. What about the mesoplastics characterization? So from macro to micro, there is still one additional step, which Alexandra also said, and that's the mesoplastics. This is one of the projects where also met Andrea. It's a remedies project where Vito is partner and National Institute of Chemistry is coordinator. There I'm showing you like just one of the sampling campaign that were done together with the beach litter monitoring according to the Marine Strategy Framework Directive. So at that time, we also wanted to check the mesoplastics. Mesoplastics has been done by the ATMI. This is the NGO in Albania who is also the project and case study leader, and they were using nets and basically like we had like every 50 centimeters like the net that was used to sample the mesoplastics, and then further on we analyzed it. How the results were obtained. So once when you get the samples from the beach, of course, there is a lot of seashells, organic matter, grass, and whatsoever. So we had a very nice bachelor student who did all the manual sorting of the sample after drying for 24 hours at 40 degrees. Or we did the flotation and the steering, and you can see here that the mesoplastics was separated from the sample itself. Of course, I think it's the same as for macro. You want to check the morphology, color, the size, the polymer composition, and what I am mostly interested in is also like the elemental fingerprint of the plastics. Why? Because different elements are also present in the plastics, which are coming from the production process, but also used as additives in the plastic itself. Basically, morphology was characterized based on the guidelines, color palette as well. For the size, I have to say that we were using Saturna imaging system. It's produced in USA, and basically gives you automatically the particle size of the mesoplastics. Of course, we use the FTIF for the polymer composition and micro XRF for the elemental fingerprints. Some of the results when we are talking about the morphology and the color, you can clearly see what were colors, the foam, the fragments, and the filaments. Of course, what is also expected that we have most of our samples were fragments. I will not go more into the detail of these results. I will just show you what the particle size distribution we get for the mesoplastic using Saturna imaging system, and also the polymer composition. Here, polypropylene and polyethylene were the most abundant ones in the samples. Of course, also the mesoplastics elemental fingerprint was obtained, and there you could see that the different elements were detected in the mesoplastics. Some of them are quite straightforward, as calcium. Titania is used as additive and colorant, iron as well. We could also see magnesium and aluminum. So in general, all the elements are the ones that we would expect to be present in the plastics. There is also another technique that we did use for microplastics characterization. I think when it was published, it was very interesting, and then several groups did also try to reproduce the method and use it for different purposes. There we wanted really to characterize the low micrometer range microplastics, meaning the particles below 20 micrometers, basically to go below the range of the micro FTIF, for example. I think for those who don't know what single particle ICP-MS it is, I think most of you were maybe today also at the Perkin-Elmer presentation on the ICP-MS. So basically, we were using the carbon isotope to obtain the particle size distribution of microplastics. In this case, you can see the particle size distribution obtained by measuring monitoring carbon-13 by ICP-MS in the single event mode, and we could characterize a particle of 2 micrometer as well as 5 micrometer. In general, single particle ICP-MS is very interesting tool, although it's not meant to measure the microplastics. These instruments were mostly used up to now for the metallic nanoparticles characterization and analysis, and they are very powerful. But I think this breakthrough was very interesting, and then we have seen a number of publications using this technique to show microplastics presence in the cosmetics, for example. Mostly, let's say, in the consumer products where the concentration is quite high, because in order to use the single particle ICP-MS, you need a high concentration of the microplastics in your sample, although for the metallic nanoparticles, it's another story, like you can really go in the nanograms range. Again, the metal fingerprinting as approach to detect nanoplastics. This is why I was interested in the fingerprint of the plastic per se. Here you could see the results of the nanoplastics which was produced in our laboratory. That plastic contained titanium as an additive, and basically by measuring the titanium as an additive, we could obtain the particle size distribution based on the titanium. So basically the titanium particle size distribution can be then correlated to the nanoplastics that was produced. I thought that I also did add the SAM image, but I think I did not do it. I think now, yeah, like a lot of metal doped particles are already produced for these different exposure studies, and also single particle ICP-MS method tracing different elements in this kind of the doped particles is a very well established method. What about the nanoplastics characterization? Here I will give you just several case studies. So one is on the simulated UV weathering of disposable plastic face masks. This small project has been done through the short-term scientific mission funded by Cost Action Priority, and also the Nexus Monarch project. We had a student who did a simulated UV weathering of disposable plastic face masks, and then after simulation of 5, 10, 20, 30, 50, and 1 year of sunlight exposure in the Thessaloniki, we did try to analyze samples, the leachets, and also the masks after the degradation. After the completion of the weathering in the UV chamber, as I said, the samples were taken and we performed analysis by using different analytical techniques. What does it mean? For the weather mask, we used the FTIR and the pyrolysis GCMS in order to see which are the changes of the polymer after the weathering. And for the leachets, we wanted to check the particle size characterization with the microscopy, to check the form fibers and particles, and of course to check the topography by using atomic force microscopy. As we have seen that that we could not estimate measure particle size characterization by dynamic light scattering due to the low concentration of the particles in the samples, we did extra UV tests, and after that aging, we also performed again the DLS measurements, where we could then clearly analyze the samples after extended then 1 year aging of the face masks, and there we also use the symmetric field flow fractionation as a separation technique. Here just some small results. You can see here how the plastic particles are released after 50 days. also by AFM, how we can detect the nanoparticles into the solution. And of course, what is very interesting and the method that we are using more and more now in our laboratory is pyrolysis GCMS. That's I think also here in Serbia, at least I know that Alexandra Laboratory is also having. Here you can see that the masks are mostly composed of the polypropylene, and we could estimate the mass of the polypropylene released from the masks during the weathering at different time points. So you could clearly see that at certain point after 1 year, we could also measure around 35 milligram per liter of the polypropylene. I have to say here, I'm just showing you like some results that we have, but of course we also did try to compare different methods to analyze the same results. And what was very interesting that with the different analytical tools, we can see the trends, but we could not get really like one-to-one concentrations. As of course we can explain it to some extent, but yeah, like in general, I think based on the analytical on the question you have, you will use different analytical methods in the end. Of course, yeah, one of my favorite techniques, because I did a lot during my postdoc on the method development of analysis of the metallic nanoparticles. Now we use it also for the UV weathered disposable plastic face mask. After accelerated weathering, once when you see it at the DLS, you can also then analyze it by using the field flow fractionation coupled to the multi-angle light scattering. And then here you see that let's say the radius was around 150, meaning that the particles were around 300 nanometers, which are released after the UV weathering of the masks. What else? In the recent project, we are trying to test new materials, especially the textiles. So we are trying to compare the PET textile with the recycled PET textile. This has been done within the SSBD for HEM project. There we are using the ISO standard washing procedure, which can be done in one of the institutes that we have collaboration. After the washing step, then we try to analyze the release of the particles. We could clearly see that standard PET and recycled PET behave differently, that recycled PET released more particles as well as fibers. And what we are currently doing is now with the pyrolysis GCMS, we want also to quantify the mass balance in the samples itself. From our side, we don't use much micro FTIR. Micro Raman we have in-house, micro FTIR we still don't have. So we are currently like really trying to go more into the detail with the pyrolysis GCMS, and we are using a lot the AFM for particle size distribution determination. What we have still, we were trying to develop also some methods, especially the field flow fractionation, where we wanted to separate the particles to obtain the particle size and then to characterize it by polymer composition. Here, yeah, like with a group of collaborators, we did propose one very interesting concept where we can use the multi-detector field flow fractionation for nanoplastics characterization. Of course, we could use the online detectors, but then collect the fractions and do the offline analysis, and then of course use the pyrolysis GCMS or any other techniques to derive the polymer composition after obtaining the particle size by different detectors. On the spiked fish samples after digestion, we could clearly see that we could determine the polystyrene size. Here from the radius, you could clearly see that the radius of particles is a bit higher than 40, and we were using 92 polystyrene sample to spike the fish. But I also want to show you like this line here, because this is like just the pure fish sample. You see if like the fish sample is like not spiked with any of the materials which we used for the method development, you could clearly see that the method will fail to see the particles in the sample, and then further do the solvent extraction and the polystyrene identification and further quantification. So basically, these are, you know, like all these different complementary techniques that we can use. I call it integrated approach, and I think that it's very useful, of course, for different purposes we do and have in our lab as questions coming. And maybe one of the very last one is the sewage sludge. So basically, I have to mention that Parology GCMS method is really like powerful tool for the nanoplastics detection, and also the low micrometer range plastics particles where we are out of range of the micro FTIR. Of course, yeah, there is like a huge palette of literature already available. Of course, the sample preparation step prior to instrumental analysis is also very important. Here, our PhD student is working on different samples. Method is developed, so we are quite sure what we are measuring, the quantification, but still the sample prep for different matrices is very, very challenging. I think Maya also knows, because we were working also a lot together with Geraldine on the samples. However, yeah, I'm showing you here just like one of the samples that we had from the sewage sludge in Belgium after the extensive sample preparation, which was required. We obtained the pyrogram, and then of course we analyze it further. These were like the polymers that we had, and basically, which was very interesting, is that we also did manage to analyze the polymer concentration in different samples. In this specific case, we were mostly interested in the tire particles, and then we used like the special marker for the concentration of the. Of course, yeah, these are all ongoing. They will be future, because like ISO standards are also putting Parology GCMS as one of the methods that can be used. And maybe finally, something which goes beyond the nanoplastics, and actually these are the additives and leachable compounds. There is a lot of inorganic particles as additives in the plastics, but also a lot of organic. We already know for the phthalates, which can easily be leached out of the plastic products. Currently, under the upstream project, we are using the very fast screening technique, where we can, of course, build the database of different leachable compounds, and then for different materials in the leaching. We had also like some different like the gloves were aged after the surge of also check the oxidation state of these materials. So going more into the depth and the processes, what's going on during the aging. But this is something that that is coming, I think, more and more. We are aware, okay, the microplastics is released, the nanoplastics is released, but I think on the human health, what is most important are actually like the leachable compounds coming out due to the weathering or the use of the plastics. By that, I think I am almost done with some messages that I think don't differ much from your presentation. Of course, yeah, like depending on the particle size, you will use different analytical methods. Of course, the environmentally relevant samples are more complex. We have, of course, to have the standardized sample preparation method. Alexandra already mentioned, like that there is not much standardization. Intox is working a lot now on the in the future for sure. For us, we have like the Raman in-house. I also think FTIR are quite well established. There is a lot of improvement, especially on the automatization. Pyrolysis GCMS can be a very powerful tool. We are also using the atomic force microscopy. You know, like it really depends on the characteristics and the research question you have. And of course, from my side, I think we have also to look into the future and also into the leachable compounds and how to detect all the chemical additives during the degradation of different plastic products in the environment. By that, I have to finish my presentation. I have to thank my group, to PhD students, Artem, Dazzle, AFM, Nina, the stay here and giving me this opportunity. And these are like some of the projects that so from environmental samples.
Možeš to ostati? Da li imamo neko pitanje iz publike sada?
Just a quick question about the web UV web. Is there a standard definition for how you weather polymers? I'm kind of interested because you know a lot of the FTIR libraries that we base these on are non-weathered polymers, and it was something that I was thinking of doing, but I'm wondering if there's a standard definition for how they should be weathered.
So basically, you know, there were several research groups which were doing like the weathering under this, because like the chambers are part, and they are like some ISO standards for the weathering per se. So and then you can calculate. Of course, you have also different rays, but yeah, like I think what I see now here, it's not like 100% one-to-one what happens into the nature, but by FTIR, for instance, some plastics which were weathered. And you make them analyzed by the FTIR, you don't see the changes into the spectra. But as soon as we put it on the pyrolysis GCMS, it's, you know, like more sensitive, and then you already see it after a few days that changes occurred that, in the oxidation. So of course, if you want to build up your FTIR database, you have to weather them maybe like more often, more like longer. But yeah, like indeed, there is quite a lot of literature. I think also the Sebastian Pinke, he also developed the database, which is also like openly available. They are also like the weathered plastic polymers were included there. So like science did a lot, but yeah, like. For the weathering per se, there is, you know, like there is a standard method for weathering in the chamber. So you are buying the chamber. We are like a lot of different, especially plastic producers or different products producers. They are just using them to do the weathering of their products. So that's quite well known.
rather than buy one, I might try and find a partner to partner with to work with it. But no, but thank you.
Yes, yeah, we do. Yeah, like we do it the same. For example, like for extensive weathering, I have like the UVB, for instance. It goes, you know, like very fast. You see what's going on. Dina did this weathering in Thessaloniki at the university. We have also a collaboration with the DTU because yeah, like when we wanted to buy the second hand, we were, you know, like taking out the straws, who will do it, and then yeah, like this is how it goes. But you know, in companies who have products, they have it there and they just do it on the regular basis.
Thank you.
Another question?
Thank you for the presentation. I have two questions. For the sample preparation, when you measure particle size for nanoplastics, is there you remove the larger particles because using BLS or A4F will be a problem? And for the second question, you mentioned that you have also tried to couple techniques for fracturation, like one, and you find challenging different fields, but also in range you can use centrifugation, the gradient centrifugation, DLS, and
similar as the DLS, also to characterize the particles, for example. I mean, like it is just, you know, like too many techniques, so like we concentrate to certain ones where we are sure that somehow have potential, you know, like to analyze.
You can come and write the answer if you're willing. I'll wait here for you because now we have an activity for you guys. Sad ću ja opet na srpskom. Za vas smo pripravili malo sad da se prije nego da dođe Ula da vam predstavi svoj rad, mi ćemo za vas pripremiti jednu nagradnu igru da budete mogli dobiti nagradu filter za vodu koju ima Hakim Vani i to ćemo uraditi potom Slido quiz. Tako da sada uzmite svoje telefone i onda ćemo početi s kvizom. A pitanje će vam postavljati Špela.
Ali prvo, znači, za ovu nagradnu igru prvo vam treba još jedna osoba. Znači, ovu igru igramo u parima. This game we play in pairs. So you need one more person. So get up and find one person that you can play with. If you want to win an amazing prize. So you need one phone and another person. So you will have, so this is of course if you want to ask.
I don't know.
Znači svi koji želite igrati ovu igru, trebate imati još jednu osobu i onda se sa jednim telefonom logirate. Znači i u ime kao Špela i Andreja, znači treba staviti vaše ime i piše vašeg partnera.
Da ne radi, šta? Radi, dobro. Dve osobe u jednom profilu. Evo vas, tu ste. To su sad parovi, a? Dobro. Ajde, možemo? Ne? Njemu rabi pomoć. Ok, možda samo da kažem da ovaj koji pobjedi dobije nagradu? Da, a pošto ti razložila? Da, ovaj par, ili?
Da, taj par koji pobjedi, ovo je dobio nagradu. Zbog toga smo pari.
I
pitanja, i ako odgovorite pravilno na sva tri pitanja,
i što brzi ste, više puta points dobijate, tako brže odgovarate, bolji ste, ok?
da li smo spremni?
Ne. Čekamo još jedan par. Ajde, Vesna, ajde. Može? Dobro, ajde idemo. Prvo pitanje. Koji je jedan od pokazatelja lošeg kvaliteta vode? Prozirnost vode, prisutnost mehurića u vodi, neprijatan miris i ukus, temperatura vode ispod 10 stupnjeva. You should have a translator. You did?
Znači, pravilan odgovor, neprijatan miris i okus.
Ajde.
Idemo dalje.
To je pravi odgovor, bravo. Drugi, što mikroplastika može da uzrokuje u ljudskom telu? Može. Ništa, hormonski disbalans i druge zdravstvene probleme, samo promene ukusa vode, više energije i bolju hidrataciju. How can it harm? Ok, još 4 i čekamo odgovore, ajde. Ne može? Ok, to je pravi odgovor. Još zadnje pitanje, a ovo traje malo duže, tako da možete razmislite dobro. Koja je svrha hyperfiltera? Da poboljša ukus voća i povrća, da odstrani mikroplastiku iz pitke vode, da zagreje vodu tokom zime. Nisam ja pravi. Hakim, možeš. Dobro, sada ćemo vidjeti kako ste najviše odgovarali. Bravo, bravo. Sada da vidimo ko je bio najbrži. Galina i Lara su pobjedili. Bravo. A dođite sada po nagradu, dođite. A na drugom mjestu Vesna. Ula. Dobro. Koliko malo časa? 15. Ok, evo sada smo tu na našem final. Sorry, we have to be in English. Sorry. Yeah, this is our final list, but not final speaker. I have to tell Ula that your presentation from your team was really a highlight of our Zagreb's event. And that's why I decided we need you here. So, with no further ado, I would give you word. So, Ula, I will just present you on shortly. Ula, Dr. Putar, to be formal, holds a master's degree in chemical engineering and a PhD in environmental protection from the University of Ljubljana, Slovenia. She currently works as an assistant professor and postdoctoral researcher at the Faculty of Chemistry and Chemical Technology. She is an active member of the Planterastic research team, where her focus includes preparing and characterizing microplastics, simulating their environmental aging, assessing ecotoxicity and indirect effects, and developing prevention strategies. Her collaborative work spans both national and international partners, including institutions like the National Institute of Chemistry, Korea University, Technical University PIN, RPTU, I don't know what that one, and SciTech. She is also the recipient of a 2-year national postdoctoral research grant exploring how microplastics influence a nutrient cycle and greenhouse gas emissions. So Ula, the floor is yours.
Thank you very much for the invitation, and also thank all of you for sticking out. I know that we are all tired after the whole day of discussions and thinking about the microplastic pollution and the problems that we are facing also in the future. So yeah, today I will talk about more like how to prepare environmentally relevant microplastics for laboratory research. Because this was one of our first things what we did with our research team, Planterastics, because when we started to work with microplastics, this was more than 10 years ago, we also have part of our faculty, there are also material scientists. And we really wanted to know what kind of microplastics do we need to prepare to be as similar as possible to what we found in the environment, and on the other hand, to really characterize them, to know what we are facing, and to then connect the properties of these particles to the actual effects, for example. So basically, microplastics, we all know they are very diverse. We can find them in different sizes, different shapes, different materials, but not only polymers. The main problem are also the additives that can later leach from the particles. They can also have different pollutants adsorbed on the surface, especially if we are talking about microplastics, for example, in the wastewaters. And of course, these properties can also change when microplastics are entering the environment. This is what we are calling weathering. And this is one of very also important topics. So with this, we have on one hand microplastic particle that is 20 micrometers in size with the perfect sphere with very smooth surface. But on the other hand, we also have this very irregularly shaped particle that has many sharp edges, and maybe also because of the weathering in the aquatic environment, a lot of biofilms, so a lot of microorganisms are attached on the surface. And by the characterization, these particles are both microplastics. But which one do you think it's more environmentally relevant? Yeah, of course, the other one. So this is what we will talk today a little bit more. First part will be about the preparation of different microplastics for the laboratory research. And then the next step, a little bit about the characterization, and the last part about the aging and weathering, because this is something that we are doing it quite often and quite a lot. So the preparation. In the past, for example, I don't know, 10 years ago, majority of studies were using spheres, so these perfectly spherical particles with a specific size, with a specific chemical characteristics, usually just pure polymers. But like we already said, this is something that it's not environmentally relevant. It's very useful, for example, if you are developing some methods for or optimizing some methods, analytical methods. But if you are focusing on more like what is really happening with microplastics in the environment, for example, about the effects or absorption of pollutants and so on, these particles do not represent really particles that can be found in the environment. But in the recent years, a lot of companies started to produce also fragments that you can buy, that it's quite easy to obtain, so you just need to buy them, and they are very much more environmentally relevant. So if, for example, you don't have meal in your lab or something like that, then you can always use this possibility, but I should mention that they can be quite expensive, especially if you're ordering them for the US, because then you have also customs and so on. Yeah, it's true. Usually like few grams or few milligrams are like, I don't know, 400, 500 euros. So yeah, quite expensive. One possibility is also to obtain microplastics from cosmetic products. This was quite frequently used in the past, but now, for example, in the UE, they are banned from the cosmetics products, so the companies cannot use them anymore. They are replacing them with some natural particles, but I think in some of the countries you can still find a lot of cosmetic products that can contain microplastics. Usually they are like polyethylene. Here is one video. You will get the slides after the event, so you can check it. These were like, during my presentation, you will see a lot of these YouTube links. These are videos that we prepared 2 years ago or 3 when we were doing one summer school in Netherlands. So they are just like, actually we were recording it by phone, but it was just to mimic how you actually can do these different preparation techniques. So you are welcome then to check it. Much better is, of course, if you are preparing particles by yourself. One possibility is bottom-up approach that is not really commonly used, maybe by some chemists, so that you are preparing particles with the chemical synthesis. Usually you're having some monomers. Doing the polymerization, you're getting synthesized microplastics. Are they environmentally relevant? Yes, for sure, more than spheres, but still they are not so good because usually they do not contain any additives, and also a lot of them, they are usually more like in shape of spheres, and of course characterization is always needed. And like I said, this can be quite challenging because you need special techniques and special knowledge to do it. On the other hand, top-down approach, so fragmentation or milling, is, I think, nowadays the most frequently used method for the preparation of microplastics. So basically, you can have whatever plastic item that you have and mill them to get usually fragments. You can also use some pellets, for example, so this semic product, and you can also mill it. If you are using the plastic items, then of course you need to first scissor it. These are the most common mills that are used for the fragmentation: centrifugal mill, ball mill, blender mill. Blender mill is usually not so strong, so mostly researchers are using centrifugal mill and ball mill. We also have in our lab centrifugal mill. With the ball mill, you usually can get particles of lower size than with centrifugal mill, but with the ball mill, you usually have these balls that are from some specific metal, so it's a possibility that this metal will leach during the milling and be absorbed on the particles. And of course, during the milling, some of the mechanic force is also transmitted to the thermal force, so mill is starting to heat up. So always you need to use liquid nitrogen or dry ice for the cooling of the plastic item that you are milling, and of course also cooling the mill. We are always suggesting to use liquid nitrogen instead of dry ice, because dry ice can be also contaminated with microplastics quite a lot. So, and of course liquid ice can have lower temperatures than dry ice. These are just two videos that you can also watch later, how they are, like, what is the principle of two different milling techniques. But after the milling, of course, you should somehow separate particles, larger particles, smaller particles, especially if you are using the ball mill. So this can be done with the sieving. Actually, what we are usually doing, we are sieving particles to remove larger particles, but on the other hand, also to remove the smaller ones. I will show you later what was happening in one of our cases when we didn't do that. So basically, also to remove the smaller particles, depending what is your research question and what do you want to have for the particles. So for example, in our case, sometimes we are using, I don't know, sievers from 500 micrometers till, and then the next one to 250 meters. So we are getting the particles of this specific size range. With the fragmentation, you need to be careful because you will never get particles of just specific size, like you are getting it with the spheres, for example, that you get spheres that are 100 micrometers. You will always get some size distribution with the fragmentation. These are just few examples of the preparation of microplastics, so we can move on to the characterization part. Of course, basic characterization of the shape. It's quite easy to, if we are talking about the larger particles, of course, quite easy to use light microscope or stereo microscope to determine shape and maybe some parts of the morphology. And on the other hand, of course, also electron microscopy to also observe surface morphology. Of course, in our case, we are usually using scanning electron microscope. It's also much easier because with the transmission electron microscope, the electrons need to go through the sample. So this means that you actually need very thin layer of the sample. So it's not really useful if you want to observe the morphology. So transmission scanning electron microscope is a better choice, but you always need to coat the samples before. Because of course polymers, they are not electronic conductivity, so you need to increase that with some coating with some metals. And you can see here it's quite interesting because, for example, these are nanoparticles that we bought. They should be, I think, 25 nanometers, but you can see that they were like larger or smaller, and like not really the ones that they are labeling it. But what you can also see with the scanning electron microscope, for example, this is the surface of the PVC after UV aging. Before it was just a smooth surface, but after UV aging, you can actually see the initial of the fragmentation and damaging of the surface. And in this case, this was biodegradable PBAT after UV aging and then biodegradability test, so also exposing microplastics to the microorganisms. And actually microorganisms start to degrade these particles, and you can see here these holes were not present before, so when we were observing the pristine particles. With the chemical characterization, of course, you can use different methods. We heard a lot of them already today, so maybe I will just more skip this part. We are usually using FTR for the chemical characterization. Here are just to mention, usually if you are having the machine, of course, you're also getting some libraries from the producer. But there are also available some free libraries that you can also use if you don't have access to some other libraries, and of course also the articles. We are using also scanning electron microscope coupled with the EDX to sometimes to determine if there are some pollutants adsorbed, so to determine some elemental composition. In this case, for example, you can see here that polyethylene with adsorbed nanoparticles, titanium dioxide nanoparticles, that you can clearly see here titanium, and this is oxygen. And in this case, there were polyethylene that were modified with the magnetic fluids, so with the iron, because we are now testing if it's possibility to use magnetic microplastics for the easiest separation. And here you can actually see, so these are these particulates that are adsorbed on the surface of the polyethylene that are indeed iron and also some oxygen. And size analysis. This is something that we are quite passionate about. So how can you determine size analysis? The very simplest way is sieving analysis, but you are usually getting just size fraction of the, you're getting, so the weight of the specific size fraction depending what are your sieves, so what are the sizes of the meshes. Of course, optical stereo microscope or also scanning electron microscope can be useful, but they are very time consuming because you need to measure at least, I would say, 100 particles to get at least a little bit reliable data on the size of the microplastics. Of course, DLS here, it's maybe not mentioned, it's also quite commonly used, and one is possibilities also laser diffraction analyzers. This is something that I will also present you afterwards, because this is also one technique that we are usually using it. So how can you then determine the size? Of course, you should always mention some mean size and standard deviation. Some of the articles are sometimes mentioning just like what is the minimum or what is the maximum size of the particle. And the most, maybe the most good to really show what kind of particles do you have is particle size distribution, so that you are actually explaining or showing what is the distribution of the particle in your sample. And there are two possibilities to evaluate particle size distribution. One is by volume and one is by number. And this is quite important because usually researchers, they are not really know what is the difference, and they are somehow representing it in, I would say, more wrong way. But with the volume distribution, it's not so good for microplastic research, and I will try to explain you why. So we have this one sample that contains two particles. One particle is 1 micrometer in size and the other is 100 micrometers in size. And if you are looking at the particle size distribution by volume, so this means like how much of the total volume of the sample the specific particle occupies. So in this case, of course, the larger particle, because we have only two particles, the larger particle occupies the majority of the total volume of the sample that you have, and the smaller particle is almost invisible. And this is not something that we are interested in. We are interested in how many of the particles are in the specific size range. So in this case, the number particle size distribution is much more useful and giving you much more reliable information. So in this case, when we have only two particles, so one particle 50% is in the size range of 100 micrometer and the other is in the size range of 1 micrometer. So it's always preferable to use number particle size distribution. And I don't have here, but you can see it from before how then it usually looks like. So this is just like normal distribution of, for example, some fragments that we are preparing them, usually milling them. So you are getting the variety of the sizes, and then you can also determine from the particle size distribution also modus, median, and of course also mean size can be calculated. But with the fibers, of course you cannot use, for example, DLS, or you cannot use laser diffraction analyzer. So usually with the fibers, the best way is just to measure it with some microscopes. For example, here we have very, very long fibers. So we were measuring them under the optical microscope with the software. So actually measuring, for example, here, because it was so long, we needed to divide it into two pictures. So the first part of the sample and then the second part of the fiber, and just sum it up to get the total length of the fiber. And then similarly with the diameter of the fibers. So we are just usually measuring it with the microscope, and then after many hours of measuring, we are getting the mean volume of the length and diameter, and of course also the standard deviations. In the case of the larger particles, so we are mostly talking about the mesoplastics, or larger. You cannot really use, for example, laser diffraction analyzer anymore. But if you have some specific softwares that they can process you with the picture, we usually just take the picture with the phone, with the scale bar, and then in the AxioVision program that we have, for example, you also have many different programs. You can, so the program will detect the particles from the background. Of course, you always need to check, because sometimes they are missing some particles that then you need to click it manually, and then you can get the size distribution. And also, for example, in this case, the software is also determining the number of particles. So if you have mass that you are weighting, then you can also get the information about how much particles do you have per mass. This is how the laser diffraction analyzer is working. Here is again the video. So basically, the sample is going through this channel, and you have different lasers and then different detectors that are detecting the lasers. And with the software, it automatically calculates the size distribution, the mean number, and so on. But are our results always accurate? This is something that you always need to think about. And I have two examples. In this case, this was something that I was mentioning before. So in this case, we were first taking the picture under the scanning electron microscope, and we saw, okay, so these are the particles are relatively large. I think they were around, so scale bar around, I don't know, 300, 400 micrometers. And then we did size analysis with the laser diffraction analyzer, and we got this distribution, and the mean number from the number of particle size distribution was actually that the majority of particles were 23 micrometers, so much more smaller. And it's like, okay, so what is happening? And then you can actually see it here. There were many particles, very small particles, that were also attaching to the larger particles, but also they were here separately. And this is actually what I was talking before, because there were so many more these smaller particles in comparison with the larger particles. The size distribution by number shifted towards the smaller particles, but here is just, for example, mean volume of the mean size of the size distribution by volume, and you can see that the volume distribution shifted towards the larger particles. And if you are putting this graph more closely, if you're looking at, you can actually see also the larger particles, but in very low amount, because, like I said, many more smaller particles were present in comparison with the larger particles. And of course, what we always need to be careful about is also the agglomeration, especially if we have smaller particles that have very high tendency to agglomerate. This is, for example, tire wear microplastics, or this is some other bakelite microplastics. You can easily see that the particles are sticking to each other. So if we are measuring the size with the laser diffraction analyzer with the dry unit, the machine will just measure the size of one agglomerate, not the specific particles. So in this case, we are using, you can use, of course, for the smaller particles DLS, or we are just using laser diffraction analyzer with the wet unit, meaning that you need to prepare suspension, stable suspension, usually with some surfactants, and then measuring the size. That is usually much more accurate. Other characterization techniques or like characteristics that you can determine with for microplastics. So usually we are always also determining the number of particles per mass to have the concentration in volume and also in the number of particles in our experiments. Specific surface area, it's possible to measure, but usually microplastics, they have very low specific surface area because they are not porous materials. So in a lot of cases, we cannot really determine because it's too low. Of course, also some zeta potential, crystallinity, wettability, molar mass, density is also possible to measure, and of course, always the presence of additives with some analytical methods. Of course, depending what is your research question, then you can adjust the characteristics of your particles. And the last part is aging or weathering. This is also something that we are doing it quite a lot for a lot of other research groups. So basically, you can divide microplastic aging or weathering into two possibilities to have abiotic aging or biotic aging. So abiotic aging is usually when we are talking about some aging, for example, some accelerating aging, some oxidation, some mechanical damage, and you can do it in some chambers. This is also what we already heard about, to use some Suntex tests or also to do some chemical oxidation, for example, with the Fenton oxidation, hydrogen peroxide in combination to UV light and so on. The other possibility is, of course, laboratory approach, so that you are actually simulating natural conditions. This is what we did in one of our previous studies. For example, we did abiotic aging in the medium that is very similar to the fresh waters with the UV lights, but the intensity was similar to the, I don't know, usual some UV light in summer in the Central Europe. So we didn't do accelerating aging, but just normal UV light intensities. And then we did some additional experiments. And one possibility is also outdoor approach. These are not microplastics, they are tiles, but still I know from reading a lot of papers about aging that some researchers, they're doing also outdoor approach of aging, so just putting some particles, for example, on the roof. But of course, there is always a chance that you will lose some particles during some, I don't know, heavy raining, wind, and so on. On the other hand, biotic aging or biofueling is when microorganisms are attaching on the surface. They really love to attach to microplastic particles. This is usually we are talking about abiotic aging mostly in the aquatic environment, but of course also in the terrestrial environment, because also microorganisms are present in the soils. You can have some biotic aging. So basically what this means, usually first is first layer of some inorganic and organic substances are adsorbed on the surface of microplastics. then this surface is even more attracted for microorganisms that start to attach, first with some weak forces, and then they are starting to excreting extracellular polymeric substances, EPS. So these are like different polymer substances like proteins, carbohydrates, and so on, that stabilize the biofilm, and in the end you are getting quite stable biofilm. Here you can see on this picture from the optical microscope, so we have very irregularly shaped, I think this was polyethylene, and then a lot of microorganisms attaching on the surface. Here with the green it's visible, these are algae, but also some bacteria, of course, were present. But not only microorganisms, also, it's working, also higher organisms, like here you have rotifer, can be attached. This was actually video from the optical microscope when we were taking these pictures. This rotifer was attaching to this particle and just waiting to some algae to come near, and it was just eating it. So it was like quite interesting to see this rotifer attached to the particle. So how can you do biotic aging? We have natural aging, so in the environment, but of course, again, you need to be very careful about losing the particles. Here you have many, this is from one of other studies. Usually they are aging in the environment, some larger pieces of plastic, not microplastics. But on the other hand, you can do biotic aging in the lab, for example, with some specific monocultures or combined approach. This is something that we are doing it quite often. So we are collecting natural stream water, fresh water from the environment, taking it to the lab, and then exposing microplastics to this water in the lab under control, on control conditions, like controlling the light, the temperature, usually on some orbital shaker, and just changing the water, I don't know, every week, every 2 weeks, and so on, to get this beautiful biofilm and particles that are aged that can be later used for other research. And how then this actually looks like, something like this. Okay. This was one very big aging experiment that we did. As you can see, all the shakers were fully occupied. And this is something that then we can also do. So aging them for several weeks and then do some additional experiments with the aged particles. So to conclude, of course, you can do different studies. So you can have some studies when you're developing some advanced methods. You can do some ecotox, interactions with other contaminants, investigating fate of the behavior in the environment, and so on. So always you need to think about what is your research question, and then think about what is the best approach, what is the best particle that you are using. Like I said, if you are developing some analytical methods, then of course the first thing that you will use are spheres. But on the other hand, if you're doing some more environmental studies, then of course you should always have environmentally relevant microplastics, and of course you always need to characterize them, because only with the characterization we can really connect these specific characteristics of microplastics with the specific effect that you can observe during your experiments. And with this, I would like to thank you for your attention. Of course, also thank you to our research group in Ljubljana. If you have any more questions, of course, you can always contact us. You can follow us on social media accounts. And if you will need some help with the preparation of microplastics, we are already milling it for the half of Europe. So we are very happy usually to help you with, I don't know, preparation, characterization, and so on. So you are very welcome to get in touch with us. Thank you again.
Da li ima neko pitanje? Haydi haydi.
Tired
Haydi haydi. Evet.
Thank you for the nice presentation. Can you please clarify how do you treat the accumulation of microplastics? Is one size the highest one, or?
You mean for the characterization?
Yes,
or?
yes.
Yeah, usually to determine the size, this is the main issue, because if they're agglomerating the particles, then you cannot really measure the right size. So we are usually using the surfactant, I think SDS. I'm not sure about the concentration, I think it's 0.1%. In the water medium to separate the particles from each other, and then usually we are getting the okay results. This is like more for fragments, for example, and also spheres.
Can you maybe also state your name? I mean, yeah, okay. Thank you.
My name?
Да.
Mirani Chuzuroshes from Institute of Physics, Berkeley.
I have one question. You mentioned in the example when you compared the number and the volume-based distributions, you said you are not interested in volume-based distribution. Why is that? Because when we are making the risk analysis about exposure, we would like to know what is the mass of the plastics. Because when you have 100 times larger particle, it means 100 larger volume and also mass. So why we wouldn't like to know where the mass is?
Here we are talking about the characterization of particles that we are preparing it. So you need to know what is the number of particles of the specific size. And if you know what is the number of particles, so for example, you have 10 particles that are 5 micrometers, 10 particles that are 10 micrometers, 10 particles that have 20 micrometers. And then with the volume distribution, this can be hidden because you're only having like what is the volume, the percentage of the total volume that one particle occupies.
Yeah, but it carries the mass.
Yeah, of course, but
If
you can then.
an exposure, let's say, we think that population would expose some organism or whatever, then we would like to know where the mass is. It's like when you have a truckload, 1 ton of plastics, and you are interested in only 1 gram, and the other 999 kilos you're not interested in.
Yeah, but this is mass, this is not volume.
But the volume and mass are related.
Yeah, that's true, but you also, if you have the characteristics determined, so the number of particles per mass, then you can easily calculate also what is your mass regarding the exposure.
Yes, but it's another. Okay.
Yoshneko, is there any questions? Any more? Online, it doesn't look like. No? Okay. Then thank you, Ola, again. Maybe we can continue the discussion in our last part of the event. So I will stick to English since we're having also online colleagues with us. So thank you very much. We are bringing now this event to an end. First of all, I would like to thank you guys for staying with us the whole day, for paying attention and for your energy, for giving us your feedback, for giving us your good vibes. I loved it today, so thank you so much. We heard a lot of new things, I think, and I hope you learned something new and you met somebody new and that you made some new friends, some new colleagues. We had seen so many different fields of microplastic research, from micro to nano. We even covered some macro and meso. We had pitch sessions where you could see who is doing what in the region. We have wonderful demonstrations. As I hear, people were thrilled. And I think our community is growing, slowly is growing. So I love that. That's really cool. I ask you to stay in contact. please, I will keep you all in our newsletter, so I will keep informing you about the events that we're organizing in the region, and I would love for you also to inform me about what you're organizing so I can share this information widely. And last but not least, there's still coffee for you in the room with catering, so you can stay as long as you want, discuss, investigate further, and welcome to Slovenia as well. I feel like the Samo jedan. Akademija, da vas puno pozdravila.